Okay, so the paper that we're presenting is called 2DFQ, two-dimensional fair queuing for multi-tenant services. It's by myself, Omar Hussein, and Fei Chen Liu. And what 2DFQ is, it's essentially a scheduling algorithm for processes or applications running in a cloud, in a shared cloud environment. And one of the things about parallel computing is all resources are shared because it's running essentially in a shared environment, and you have multiple requests from users, and which I guess moving forward we're going to be calling tenants. And what we want to do is we want to make sure that each requesting entity gets an equitable share of the resources, right? We want to make sure that there's no process that's kind of left behind or that isn't getting that isn't getting the resources that it needs. We also need to ensure that there aren't some processes that are just waiting interminably, right? That are forgotten and are really low priority and they never complete. You could start getting more and more of these tasks building up and wait and backing up, which could cause high load or some kind of failure. So one method to service requests like these is to use what's called fair scheduling. And the definition is basically in the name, right? In essence, you don't focus on only one request beginning to end. If you have three requests, you work on all three. Um, and so what you'll do is you'll work on one and then you'll say, okay, I should stop and I should move on to the next one. And then you move on to the next one. And you kind of cycle through the processes that you have in the current queue. So how do we decide to define fairness? Well, basically what you do is you have a set period of time and you try to make sure that each of the processes that you're swapping between, that they each have the same amount of resources over that period of time. Now, the question is, can this type of scheduling be applied to a parallel computing environment? Before we talk about that, though, I want to talk about a little bit about the history of fair queues, where they came from, and what we're trying to, and how I guess we're trying to adopt them to a shared computing environment, right? So the first thing is a lot of fair queuing variants come from network scheduling. So you'd have multiple senders and they're trying to send their information through a link, and you want to make sure that you address each of these requests fairly. Now, the way that they would define fairness was they would say, okay, it's the same amount of time for all the senders. So essentially, what is the total number of packets that you're trying to send divided by the number of senders? And that's the rate at which each of these senders would be serviced. So this was about network, like this fair queuing started to as a way to address network scheduling, but you can see how it can translate into tenants on a cloud. Now, a couple of things to keep in mind is that maybe we don't want to give each tenant equal time always, right? Sometimes someone might be running, a customer might be maybe higher priority or the work they're doing is higher priority. So we want to have a little bit of flexibility in terms of saying, okay, maybe this thing gets more resources and this one gets a little bit less. So one of the variants of fair queuing is called weighted fair queuing or WFQ. And it is fair queuing, but it can prioritize. And essentially the way it does that is it assigns a weight per process. And it's something similar to this image, right? You have multiple buckets and you say, okay, this bucket where maybe it has a lot more processing to do, so we're going to assign it more resources so it can run a little bit longer, or this one has a little bit less processing to do, so we're not going to bring it up in the queue as often. Another variant is, or I guess almost an extension of WFQ is WF2Q, or worst case fair weighted fair queuing. And WF2Q, what it will do is it will take virtual time and system time into account before it starts scheduling, before it starts to queue in some of these processes. So a couple more details about For queuing, the first thing to keep in mind is we will have multiple threads running or multiple workers running that'll essentially will use to address the needs of these tenants, right? And what you want to do is you want to make sure that all of your threads are servicing some process all of the time. Otherwise, it's wasted time. It's just sitting there. It's not doing anything when it could be working on a process and trying to finish the work on that. The other thing to keep in mind is I mentioned this earlier of virtual time, and what virtual time is, it's a way to see what process should be run next, right? So the scheduler is essentially it's judging when the work will be finished based on the start time and the request size and the weight that we've assigned to that request size, and based on that, the process will it'll pick the process that will finish the quickest among the pool of processes that are waiting for us. So then the question is, well, how do fair queues perform? And honestly, they do okay, right? But they have one issue, um, which is that they are prone to bursting. And what bursting is you have one small request and or maybe you even have multiple small requests and you have one or two larger requests, right? And because of the way that these scheduling algorithms are written, they're going to say, okay, the small request will get a specific number of times, so I will run it back to back to back to back multiple times. And then it will go to the back of the queue and it's going to wait for a considerable period of time while I run these two very, very long processes. Um, and that's essentially that's bursting, right? Is it's running something um, multiple times and it's bringing it to the front of the queue multiple times, and then it ignores it for a considerable period of time. Um, and really, I would I don't know if I would say it's by design, but it's essentially fair queuing isn't meant to prevent bursting. What the criteria for fair queuing is it's really just trying to keep everybody working at roughly the same or to keep all of the work at roughly the same level, right? If something is lagging too far behind, it's going to try to pull it up. If something is too far ahead, it's going to try to slow it down. So it's almost like running in a hula hoop. Like you have a little bit of degree of freedom, but you're not running too far ahead of everybody else. So the question then is, hey, can we translate some of these algorithms over into a cloud computing system, right? A thing to keep in mind, though, is that parallel processing has its own additional quirks, right? So the first is resource concurrency. We talked about this before, but the packet scheduling algorithms were really meant for a system that only dealt with one outbound packet, right? So we could look at the queue one by one. But here we have processes running in parallel. So how do you define and say, okay, the there are four processes running. This is their wait. This is their scheduling time. This is the ones I should focus on now versus the two queued ones that are sitting in there. The next thing to keep in mind is cost variance, right? For cost variance, essentially, um, we could run a small request in a cloud environment just to test something, and then we run the same request, but now we're trying to push or process more information. And I mean, I feel like I'm kind of running into this now with the project we're working on, where it's like, okay, I'm just going to test a very small amount, and then once I have everything working, I'm going to test with the entire set of data, right? The next thing is in a cloud environment, you could have very unpredictable costs. We don't know how long the work is going to take, how intense the work is going to be until it's requested. So I can't estimate, hey, this is how much time I should assign to this, or this is how many resources. So these are just a couple of things in the background that we need to keep in mind when we talk about scheduling things in a cloud environment. So the question then is, okay, I understand what kind of behavior should we be striving to um, should we be striving for our scheduling algorithms to achieve? And I would argue, or I guess the paper argues that it should be smoothness, right? And it's smoothness is essentially it's the antithesis of bursting, right? So it's consistent work on a task. So instead of one process hogging all of the resources and then dropping to the end of the queue for a long period of time, we kind of want to have a smooth and consistent usage of resources. So here you'll see you have your two long processes alternating, and immediately above that in a second thread, you have the two shorter processes alternating. So everybody's kind of working without being left at the back of the queue for a considerable period of time. Now you could say, okay, smoothness is ideal, but how do you achieve it? And the difference between, I guess, or what fair queuing does is, or WF2Q and WFQ is they look at the worst case bounds, right? But what we're going to do is we're going to ignore the worst case bounds because it could. Worst case bounds are just in a parallel system, especially, they have a very high possibility of being very, very intense. So instead of trying to achieve a better schedule by trying to pull back and prevent a worst case bound, what we could do is we could say, okay, so the worst case is going to be very processor heavy anyway, but how about on average, we try to create a smoother schedule. So for all of the non-outlier tasks that we're getting, maybe they can be set up to run equitably. And that's what we're trying to do with 2DFQ, right? Essentially, it's hard to be smooth when runtimes are unknown. Um, so if I get a request, for example, to come to campus for an exam, usually I know that, hey, it's going to take me maybe an hour if I leave from work, right? But that's when I'm leaving from work. In this class, I have to leave from home, so it's a little bit harder to judge the time. Uh, and I'm leaving on a weekend, so I don't really know what the traffic is going to be like. So it's very hard, similarly, to estimate job length when it's unknown. And 2DFQ has two main methods of dealing with some of the complexities that we talked about. The first is concurrency. And what this is going to do is it's going to say, okay, instead of looking at all, ignoring the size of the request that you're getting, what concurrency does is it says, okay, I'm going to create multiple threads, and there are some threads that are dedicated to focusing only on the large requests, or there are some threads that are dedicated to prioritizing the smaller requests, right? And the second thing 2DFQ does is it 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 has what's called pessimistic cost expansion. So essentially, if it doesn't know how long a process is going to take, it's just going to assume that it's going to take a very, very long time. So going back to the earlier example, um, the idea is, okay, I don't know how long it's going to take me to drive to campus from my house, but maybe I'll leave 30 minutes earlier than what I think it'll be or whatever. And if I'm wrong, right, if 2DFQ is wrong, then the resources are released earlier, which is not a big deal, right? So, but if I'm right, I didn't undercommit and block the resources to others. So some of the challenges that we would run into in a parallel processing environment is cost variance, right? We've already mentioned this, but you can see here in some of these graphs where you have a tenant that has an outlier request that is really, really large, and while the rest of their requests maybe don't go and reach to that extent, right? And what that might cause is bursting, right? And bursting by definition kind of occurs where you have one large request, but then you have multiple smaller requests. And so in WFQ and WF2Q, what happens is you'll have all of the threads working on the large request, and then they'll ignore the smaller requests. And then they'll work on a bunch of smaller requests for a considerable period of time, and then they'll drop that and work. And what 2DFQ will do is it will say, okay, I have I have multiple workers, and some of them are going to prioritize the large requests, and some of them are going to prioritize the smaller ones. So we're trying to smooth out. So that's one of the ways that it tries to smooth out some of the resource dedication. The next thing is you run into things where, and again, we talked about this earlier, is hey, you have an unknown cost, right? So estimating a cost is a huge concern. But if you're doing what's called pessimistic cost estimation, you could say, okay, I assume that I've never seen this request before. I'm just going to say that this will take an incredibly long period of time, so I'm going to over dedicate my resources. So you can kind of see um, this comparison that they have in the paper where they're talking about, okay, so for WFQ, this first chart, it will show you a little bit of bursting, right? So you have your smaller requests being chunked out, then you work on your two larger ones, and then you work on the smaller ones as again. WF2Q, right? It starts with a smaller request, and it goes back into the WFQ behavior where now it's working on the larger one, and then it goes back to the short request and then back to the longer one. Whereas 2DFQ, you can see it will split the worker threads that it's assigning. So you will have both the large request and the short requests being run back to back. So it's not just focusing only on using both threads to work only on a large request and then splitting back. With that, I'm going to pass on the next section to my partner.